Well, good morning. Everyone is back for session number 2 of this morning. We welcome our speaker and thank you for sharing your expertise and research with us today from many countries. And today we will listen to Giuseppe Cesare Lama at the top, Gabriela Di Carlo, Camilla Alves de Rezende, Camilla Enriquez Maya de Camargo, and Romain Borde. I will start with our first speakers, Giuseppe Cesare Lama. You are currently a temporary researcher at IPCB, National Research Council in Portici. You're a graduate in material engineering, and you earned your PhD in industrial product and process engineer at University of Napoli. Your research focuses on bio-based composite material, especially polyurethane foam, for application in construction, automotive, and packaging. But you are exploring possibility to replace petrochemicals with bio options and sustainable fillers like industrial waste and natural powder, but also non-isocyanate polyurethane foam, NIPU as a nickname, and foam concrete with reduced cement, and also graphene-based material for enhancing properties in polymer and ceramics. But today, your presentation will focus on innovative sustainable coating and custom-made composite polyurethane foam for cultural heritage. You've got the mic.
Thank you very much. Okay. Thank you, Stephanie, for your kind presentation. So today we will focus on innovative sustainable coatings and custom-made composite polyurethane foams for cultural heritage preservation. So, okay, I was already kindly presented, so we can skip this. At least I can show you where we work, that is here in Portici, and we share with the same office, let's say, with another institute of Italian research team. It is settled in Portici, that is very close to Naples, where I graduated. Our institute has several main area that are located mainly again in Naples and also in Catania and Sicily, but also in the northern of Italy, in Lecco, close to Milan. So our institute has several key competencies. Just for example, in chemistry, we work every day with chemics. We work with graduated in physics and specialized in polymer technology and also in nanotechnology. All of this serves for a different area, let's say, of the research that, for example, are buildings, health, transport, or energy. But today, as we already said, we will focus on cultural heritage and packaging systems. These two. So, for preservation of cultural heritage, we will focus on two different, let's say, way of preservation. First, by covering the artwork itself, and the second one by packaging. That is essentially the way the artwork is stored, or, for example, in some cases that has to be shipped. So, moving on first on coating, just to give a practical example. This is nougat. Nougat, it is what we call torrone in Italian, and basically it is an edible composite. Sorry, how to come back? Here. Instead of using chocolate, we use polymers, and instead of using pistachios, we use mesoporous silica nanoparticles. Essentially, we have to consider these mesoporous silica nanoparticles, also called MSN, as very little sponges. that are able to be complexed with several chemicals. For example, the BTA, the benzotriazole, that is again in turn complexed with several ions. In this case, we used silver ions in order to, in case the material is encountering some acid environment or some basic alkaline environment, or for example, in contact with the ions just like chlorine, it can protect the beneath artwork by complexing in turn the acidic solution or the alkaline solution. In this way, it is by the activation with the UV radiation, the MSN can be again activated and is able to protect the underneath metal surfaces. So another way the coating is made by polyurethane, self-healing polyurethane that is quite self-explainable because it is made of some building blocks that allow the material to be self-healed upon a thermal annealing. In this case, it was around 100 degrees. So when the surface undergoes to a cut, it can recover its original shape, its original dimension, and in particular the cut, just by heating it up. So after coating, we move to packaging, and in this case, we will focus on bio-based polyurethane foams. So this is how we work in the packaging system based on this material. Essentially, we select the artwork. In this case, is a little elephant, and it is scanned with a 3D scan. Then a digitalization occurs, and once the digital object is, the digital twin is adjusted in all its little spaces that are filled, we cover it with the precursors of the polyurethane foams that by blowing it will envelope the artwork, but not directly the artwork, but the physical reproduction, so that we have the perfect copy of the artwork that is saved, that can be then stored with a precise reproduction, a precise mold of its shape. Now, moving on the chemistry of the bio-based polyurethane foams, traditionally it is made of two components, the polyol and the isocyanate, that are both petrol-based. But nowadays, we are moving on and changing, in particular, the component A production by using some bio-based polyols, derived, in this case, from cashew nut shell liquid, that is, let's say, a food waste. And in this direction is moving also the industry of the polyurethane foam production. Then, with some bio-based additives, as well as some fillers derived from production from constructions, and also some other bio-derived additives, just like cellulose, we obtain the polyurethane foams, the bio-based polyurethane foams. But I want to make sure that nowadays we are working in our lab on those that are called non-isocyanate polyurethane foams. That is still the hard part to get away, to send away, that is the isocyanate, that is the very dangerous counterpart of the bio-based polyol. So we are developing now non-isocyanate polyurethane foams. To close the circle, the bio-based polyurethane foams we are producing, once they arrived to the end of life, there are also the ability to be reprocessed by compression molding. So with the application of a pressure, in correspondence also with the high temperature. In this way, we don't obtain, of course, a new foam, but we obtain a solid material that can be used also in other fields. And as you can see, this was the final product. This was the circular economy approach, but focusing on the artwork or the packaging for the artworks, we have 2 case studies now going on. First is a box in Avalis by Marcel Duchamp, and in which are basically all the reproduction of his masterpieces. And we will focus later, and also the skull of an Europasaurus. So, as I was saying, in the box in Avalis, there are 3 elements that are very delicate once it has to be handled and also to be transported or stored. That is an ampule containing 50 centiliters of air de Paris. This one is the cover of a typewriter, Underwood typewriter, and this one is the reproduction of a fountain, the masterpiece that was quite, let's say, very discussed at that time. So, as I said, we first make like Lego pieces. We make the reproduction of this very delicate part by adjusting the 3D model. And since we have only little area in which it's possible to 3D print the object, we made it just like Lego pieces. I have also some demonstrator here if later you want to take a look. Of course, we only need the voids to be filled. So we also made by 3D printing the envelope of these supports. This is the way the foam is made. A video. Also the music. Okay. I forgot. Okay. First, there are the components that are weighted and in a precise way. Even a little difference can make different reactions and can cause the foam to be more blown or with the different densities. Of course, after that, there is this mixing section. And after the truthfully mix, the mixture is poured. And then after, the foam is obtained and then is cut in order to fill precisely what is the spaces of the artwork. I think we can move on. Yes. And as you can see, this is the reproduction. That is the exact reproduction of the fountain. Moving to the Europasaurus skull is exactly the same, only that in this case we have much more voids within the skull we are considering. So once the Lego-like 3D printed modeling is made, we have now we are approaching to the pouring and the mixing of the formulation of the foam. And once the mold is obtained, we can obtain the Europasaur in Avalis for transport and for storage. So this is the overview of our approach to prevention for cultural heritage, both in when it is in the environment and when it is to be stored or to be shipped. Thank you for your attention. Questions later.
Thank you. Yeah, as the first session, we keep the question for the end of the session. Our next speaker is Gabriella Di Carlo. Gabriella, you're a senior researcher at ESMN, Rome, National Research Council, with a PhD in chemistry. Your main research interests include the development of innovative material and technology for sustainable conservation, and you are working at the development of active and multifunctional materials, mainly produced from natural waste and renewable sources. Among other things, you conduct surface studies at micro and nanoscale with correlative and multi-analytical approaches. Your activities take part in national and international projects like this one, and your presentation will focus on bio-based multifunctional coating of a tailor and long-term protection for metal cultural objects. Please.
So thank you for your kind introduction. And okay, just in the first slide, you can see our institute, which is in the research area of Rome in Monte Libretti. As you can see from the title and as introduced, I will talk about the development of new sustainable coatings, mainly for the protection of metal objects. And the different approaches can be used in order to avoid or at least to delay the degradation of metal artifacts. And we worked on two different approaches, like the creation of a stable microenvironment by developing biopolymer-based absorbers. And in particular, the focus of this presentation is the other approach, which is based on the application of biopolymer-based coatings directly on the surface of the metal object. And it is really very important to have a high transparency and to avoid any change in the appearance of the object. We start to work on this topic with the idea to prepare new formulations which are more sustainable, safe, and with a superior protective efficacy compared to the benchmark. And in our case, as benchmark, we mainly select commercial products based on acrylic resins, also containing benzotriazole. So within the NRSR project, we work on the development of new solutions based on chitosan, which is a biopolymer with a low cost, commercially produced from renewable sources, like, for example, the waste of fishing industry, and can be dissolved in a mixture of water and ethanol. So once optimized the formulation, we functionalize the biopolymer coating with nanostructured smart materials, also with the nanocarriers able to release the protective molecules, which in this case is a corrosion inhibitor, only in the presence of degrading species. So the idea is, like in the drug delivery, we can locally release the protective molecules only when and where necessary. So I will just summarize one of the main results of the previous project, because in this case, by using optimized chitosan coatings applied on bronze mock-ups and by performing accelerated corrosion treatment in the presence of acidic water vapors, we can see that we can improve the protective efficacy compared to the commercial products that we selected as benchmark. So in addition, these formulations were also used to protect silver mock-ups. In particular, we used the cerylene silver, which is one of the most common alloy used for in particular in metal artifacts. And if we look also in this case to the results of accelerated corrosion treatment in the presence of ammonium sulfide. In this slide we can see the optical micrographs. We observed that the uncoated disc is quickly degraded, and the best performing are the commercial products and the chitosan formulation containing benzotriazole. These coatings are quite transparent and completely removable because by using a scanning electron microscopy and by removing the biopolymer coating using a cotton swab embedded with water and ethanol, we cannot appreciate the presence of any residues, and this was confirmed also by infrared spectroscopy. So then, in addition to accelerated corrosion treatment, we also performed some aging treatment in a wooden box to promote the degradation, but in a more real-like environment, in the presence of fragments of paper, leather, and plastic. And after 30 months, we observed that the uncoated is degraded just after only 3 months. In the case of the chitosan formulation, we can have a certain protective efficacy, but we observe a slight yellowing of the coating. And by looking at the UV visible spectra, we observe the presence of some signals which are compatible with the presence of silver nanoparticles, and this was confirmed by scanning electron microscopy. So within the GREENART project, our target is to improve the long-term stability of the formulation, to redesign the formulation in a greener version, because we want to use a biopolymer matrix, but at the same time we want to introduce green additives for the dissolution of the polymers, and also green additives for functional, for other additional properties, like to improve barrier properties, stimulus responsive properties. So the idea is to redesign new formulation, more stable, sustainable, and effective. And by using products and components which comes from renewable sources and natural waste. So we have also a Lego-like structure of the composite materials, and we are worked on composite but also on multi-layered systems in order to have a superior protection of the metal substrate. So in parallel, within the GREENART project, we are working on 2 different aspects. One aspect is the passive protection. So we introduced into the biopolymer coating fillers which can improve the barrier properties, thus avoiding, for example, the permeation of atmospheric degrading agent, and so increasing the protective action. In parallel, we are working on the active protection, in particular on the identification of green anti-corrosion additives to replace the benzotriazole, and on a nanocarrier which can release in a tailored way the protective species and reduce also the diffusion of degrading agents. So in this slide you can see an overview of the different biopolymers that we used within the GREENART project, and in particular we are focusing our activities on chitosan and carboxymethyl cellulose. Both can be produced from natural waste. And regarding the green dissolution agents, we have selected the new molecules, and I will show you that we can improve the properties, and also green corrosion inhibitors like amino acid and other small molecules. And the objective is to consider transparency, removability, to prepare new formulations which are easy to use, to improve the protective efficacy, but also the long-term stability of solution and coatings. And so here we can see some results. For example, you can see a thick film prepared with the biopolymer, and in particular by using the new formulation, and we can appreciate the high transparency of these materials. But in addition, also the transmittance measured by UV visible spectroscopy show that we have a very good transparency. And if we look, for example, in red, we can see the signal of the previous formulation, with green the new chitosan formulation developed in GREENART, which is quite close to the transmittance of paraloid, which is a commercial acrylic resin. And we have also a very good reversibility of the treatment, which was proved by scanning electron microscopy. We performed in parallel accelerated corrosion treatment in the presence of chlorhydric acid, but also natural aging in an indoor environment without a control of temperature and relative humidity to promote the degradation. And so after 10 hours of accelerated aging treatment, we can see that the uncoated substrate is completely degraded. By comparing the formulation, we can see that in the case of the commercial benchmark, we observe the presence of some spot due to the formation of alteration products. Both the other formulations are quite stable, but if we look at the aging treatment performed up to 10 months in this case, we observe by transmittance measurements that the new chitosan formulation have significantly better long-term stability, because in the previous formulation we observe after 10 months a loss of transparency. It is worth noting that in this case we are using only formulation based on biopolymers without any corrosion inhibitor. So we want to avoid in the first step the use of corrosion inhibitors. And also in this case we have a very good stability. So the next step was to test this new formulation also on silver. And in this case we can see that I just showed the results of the natural aging treatment, and after 1 year we can see that by comparing the uncoated substrates, the substrate coated with the previous formulation and with the new one, we have an improvement of the protective efficacy. But most of all, it is worth noting that we can, from colorimetric measurement, we can see that we can avoid the yellowing, because with the previous formulation we can observe a significant increase of the parameter which take into account the component of the yellow. Here is significantly low, and the same is for the delta value, which is significantly lower. So we can improve the stability in the time, and this is what's also quantified. So to further improve the protective efficacy, we included in the formulation different fillers, like 2D materials and graphene-related materials that we received from the fourth group. And we used two different approaches. In one case, the 2D materials were included into the formulation. Another approach was to apply a graphene overlayer on the surface of the biopolymer coatings applied on metals, in particular on bronze coupon. And in this case, after we here I just show the results of the second approach. You can see the percentage of altered area after accelerated corrosion treatment. And we can see that the altered area can be reduced by applying 1, 2, and 3 layers of graphene on the surface of the biopolymer coatings. In addition, we also observe that the contact angle after application of the graphene layer increases, so we can promote and enhance the hydrophobic properties, so by increasing the barrier properties, and this justify the lower percentage of altered area. In addition, we are also working on 2 different classes of nanocarriers in order to improve the efficacy of the formulation, in particular layered double hydroxide, which can be used to locally release the protective molecules, in particular in the presence of chloride ions, and on polymeric nanoparticles, which have a pH-dependent release. And in this slide, you can see an overview of the mock-ups which were selected or in some case prepared in order to validate the new formulation. We are working on bronze, sterling silver and brass with a polished shiny surface. And you will see also the mock-ups during the practical workshop, and also on patinated surface which can reproduce the archaeological object. And in addition, all these activities are performed in collaboration with conservators within the GREENART Consortium. And you can find also some information in an interview which was published on this magazine, and on some papers which you can download by using this QR code. And now I will just show the activities that we are carrying out in collaboration with the conservators in order to validate the new formulations in a real museum environment, in particular in collaboration with the Peggy Guggenheim Museum, with Luciano Pensabene. We already prepared the different mock-ups, uncoated and coated with the benchmark and with the new formulations. The mock-ups were exposed inside the museum. And after 1 year of treatment, we can say natural aging in a real museum environment, we observe by optical microscopy the presence of alteration products on the surface of the unprotected mock-up, but also the presence of some alteration spot on the substrate coated with the commercial product. The best performing was the formulation based on chitosan. And here you can see the results of ADS analysis, which can provide the composition, the elemental composition on the surface of the mock-up. And we can observe, for example, by looking at the distribution of copper and oxygen, the presence of cuprite, but also the presence of chloride. So it means that after 1 year of treatment inside the museum, if we don't have a protective coating, we can already observe the formation of degradation products. We can also see the presence of some particles with a higher amount of carbon, so probably organic species. And we perform also additional analysis by using the scanning electron microscopy, and we confirm the presence of alteration products on the surface of the unprotected coupon. And it is interesting to observe that the presence of a higher amount of particles on the mock-up coated with the commercial products with respect to those coated with the biopolymers. And so by using ADS analysis, we observe the presence of elements which are typically present in the environmental pollutants. So we think regarding that they are probably due to the presence of dirty and powder coming from the environment. So probably we can have also like a greater antistatic effect with the new formulation, but we are go into more detail on these results, so we are still working on this. And here I can just show that the new active formulations, which were also in this case applied on bronze and silver mock-ups, and we have different we can say like a copy. So we have different mock-ups which were exposed in the exhibition room, but also in the deposit of the Peggy Guggenheim Museum, and we are waiting to see the behavior after different months. So the treatment are now in progress. And finally, we are also performing some treatment in collaboration with the Italian Ministry of Culture by applying the new formulation first on mock-ups with a shiny surface, but also with a surface patina, and after on a fragment coming from an bronze archaeological basin. And as you can see, it was divided in different areas in order to have like an uncoated surface and other treated with commercial products and with the GREENART products. So I can just anticipate that in any case, one of the first feedback was that with the new products, we don't modify the texture of the surface. On the contrary, with respect to the commercial products, like the those based on acrylic resins. And in addition, the risk of leaving brush strokes after drying is lower. So in this slide, you can see the results of the characterization of the object before the application of the products, and we can see the common degradation products typically observed on archaeological bronzes. And we also performed the colorimetric measurement after the application and after 6 months. The colorimetric parameters are quite stable, but we can just observe, for example, that the delta E and is slightly lower, but in particular the delta L, which is related to the luminosity of the surface, is slightly lower with the new formulation. And so finally, I want just to thank all my group which work on this project. And tomorrow, some of you probably will follow the practical workshop of Francesca Boccaccini. So you will have the possibility to see and to use the new GREENART formulations. So thank you again for your attention.
Thank you, Gabriela, for the new insight in coating. We go straight to our next two speakers, Camila Alves de Rezende and Camila Enrique Maya de Camargos. Camila Alves de Rezende, you're currently an associate professor at the Institute of Chemistry at Unicamp, Brazil, and hold bachelor teaching and master degrees in science from Unicamp. After a postdoctoral research, you gain expertise in colloidal and surface chemistry, polymer and nanoparticles. And at Unicamp, you coordinate the laboratory of chemistry and morphology, especially on the extraction of cellulose and lining from plant biomass for the production of fiber and nanoparticles. Therefore, you explore their application like coating film, aerogel, or solid foams. Camila Enriquez Maya de Camargos, you're trained as a scientist and hold a PhD from Institute of Chemistry at Unicamp and a master degree in chemistry from the Department of Chemistry of UFMG. You also earned a bachelor degree in conservation and restoration still in UFMG, where you investigate the characterization and degradation process of cellulose substrates in the field of conservation of books and on paper. You develop advanced material and sustainable nanotechnology for conservation, and both of you today are presenting nanocellulose-based coating and hydrogel for cultural heritage conservation. Thank you.
Bonjour. Thank you very much. I am the second Camila. And I will start the presentation and then we have the first Camila, okay? So we use agroindustrial residues as the feedstock to produce nanoparticles, nanomaterials. So we can extract cellulose fibers from these residues, and then we convert it into cellulose nanofibrils and cellulose nanocrystals. And also we extract bulk lignin in macro scale, and then we convert it into lignin nanoparticles. And our group in Brazil, in the framework of GREENART project, we focus on two main tasks: the development and evaluation of multifunctional protective coatings and the cleaning hydrogels. So we use mainly sugarcane bagasse as the source of both cellulose and lignin. And then we process the sugarcane bagasse to extract a cellulose-rich substrate. And then when we apply some treatments, some reactions, the oxidation followed by the mechanical fibrillation, for example, we can obtain a water dispersion of cellulose nanofibrils. And cellulose nanofibrils are these kind of nanostructures here. They are long and flexible. Or if we perform an acid hydrolysis, we can obtain also a water-based dispersion, but now of cellulose nanocrystals. And these cellulose nanocrystals are needle-shaped and more rigid nanostructures. On the other hand, with the residue of the cellulose processing process, we obtain this liquid fraction. It's an alkaline liquid fraction rich in lignin, and then we can also convert lignin into nanoparticles, the lignin nanoparticles. And these lignin nanoparticles are obtained by solubilizing lignin, and then we add water as an antisolvent, and the lignin macromolecules, they self-assemble into these nicely shaped and beautiful, the spherical nanoparticles. And now we will discuss the protective coatings based on nanocellulose and lignin, and nanolignin. So we combine these three types of nanoparticles to produce a water-based nanocomposite. And in these nanocomposites, the nanocellulose forms this network, the film network, with up to 90% of, representing up to 90% of the dry weight of the coating, while the nanolignin corresponds to up to 10% of the coating. And why nanolignin? Is not lignin the bad guy, right? So while lignin has this darker color, the bulk lignin has this dark color and is considered for many paper conservators as the villain of paper stability, right? Nanolignin is a bit different, not so different, but it's a bit different, because the color is more modulable and the color is lighter in the case of nanolignin. And at the same time, as the nanoparticles have so high specific surface area, the properties of lignin are more intense in the case of nanolignin. For example, the outstanding UV shielding properties, the antioxidant properties, the antimicrobial properties of nanolignin. So that's the reason we combine these three types of nanoparticles, and in fact, in the nature, in the plants, lignin and cellulose are intrinsically combined, and then we use this compatibility, this natural compatibility, to produce these protective coatings with this type of properties. So in this in this figure here, it's a spectra of UV and visible, is a technique, a spectroscopic technique. We can see the UV shielding properties of the films. So as the concentration of lignin increase from the black curve to the blue curve here, the concentration of nanolignin is increasing, and the UV protection is also increasing a lot, because here is the range of the spectrum that corresponds to the UV radiation between 200 and 400 nanometers. And then here we have a very low transmittance. It means that our coating is absorbing the UV radiation. So what is beneath the coating will not receive so much UV radiation. Here we have some results regarding the antioxidant properties of the coatings. That is also very interesting to protect coated substrates against the aging, the hydrothermal aging, for example. And here are some mock-ups, some cellulosic mock-ups coated with this type of coating, the nanocellulose, nanolignin coatings, and in comparison to mock-ups coated with paraloid B72. And we can see here that for the wood sample, for example, the color is not an issue because the nanolignin does not change too much the color. But then when we consider the lighter color substrates, the color can be an issue. But we will have the answer in few slides, okay? And here is another interesting result. We can see here that when we coat the samples, is a wood sample here, coated with the nanocellulose coating, and the micrometic texture of smoothness of the surface as well. But at the same time, when we consider aged mock-ups, deteriorated mock-ups, the application of the protective coating based on nanocellulose and nanolignin can even make the cohesion of the surface more, sorry, how to say that? It can improve the cohesion of the surface, because when we have the aged mock-ups, the surface is quite uneven, it's quite damaged, actually. So the application of the coating can be very compatible, but at the same time can restore this cohesion of the surface. And here we also assessed the removability of the coating, as it's important to have the retractability of these materials. And the results are interesting as well, because here we have the mapping of the surface before coating application. Here are some mock-ups with the coating on the surface, and then we were able to remove most of the coating with the application of a water-loaded hydrogel, for example, but you can do that with a cotton swab, with water as well. And the profile, the mapping profile after this cleaning, it's quite similar to the mapping profile before cleaning. And here is the answer. Right now, we are investigating how to reduce the color of lignin, and we have some exciting results. So we oxidize lignin, and then we could prepare some coatings with up to 10% of nanolignin that are completely colorless. So now, please, Camila. Thank you.
I love this white lignin, but I'm not going to talk about lignin. I will talk about the cleaning hydrogels based on nanocellulose, so our gels, aqueous gels, actually, or gels filled with water. So what we produce in the lab are physically or chemically cross-linked hydrogels based on nanocellulose and also on other biopolymers, which will benefit from the 3D network formed by cellulose nanofibers. So we prepare these soft gels containing proteins or polysaccharides, and then we incorporate the nanocellulose network, and we cross-link this nanocellulose network using these physical or these chemical bonds. And we will be playing with this a structured and reinforced hydrogel. We have mainly two systems that we are working with in the laboratory. So CNF, so cellulose nanofibrils with gelatin. They are chemically cross-linked using EDC or EDC NHS. I will not stress very much this chemistry, but it's something very used for compounds like gelatin. And we also work with this alginate CNF or with gluten-based hydrogels, which are physically cross-linked using calcium bath. So both chemical and physical cross-links, they work very well for gels. The difference is maybe how easily we can unbound these bonds. In the case of the physical bonds, they are easier to be rebuilt, but they both work very well. So here are some pictures of the gel. So just to show that we changed the amount of CNF, of these cellulose nanofibrils in the gels. So here is 75%, 25% of gelatin and 75% of CNF. And here we increase the amount of CNF to 50%. And here we decrease the amount of CNF, and here we decrease even more. So CNF in these gels improves the strength and the rigidity of the gels. Tomorrow we will have the possibility of touching the gels during the workshop to see how they, not how they touch like, because it would be strange, how they look like. And so for our purposes, we decided that the best gel, the gel with the best properties was the 50-50, containing 50% of gelatin and 50% CNF. We decided this by touching the gels, but we also performed this analysis here, which is a compression mechanical test using a texturometer. So it will give you compression curves with numbers to show basically what we have already seen with our hands. So based on these results, we could see that when we increase the amount of CNF, especially from 25 to 50%, we tend to improve the mechanical stress of the sample. And then we decided to keep working with this 50-50% gel. This is an analysis just to show it's X-ray microtomography. We performed it in the light source, Sirius light source in Brazil, and it's very nice to see the interior, the bulk of the gels. How are the pores? How are the fibers distributed? Here we have some. This is a very well. We tested the cleaning performance of the gel. So this is a very simple test using glass slides covered with artificial soil, and we tested how the gels could be used to remove this dust. Here, so it's just a glass slide covered with dust. Here we have two different fluids that we use to fill the gels. This is TAC, it's triammonium citrate, it's a surfactant. And this is water. So in every case, using 2 times we could remove the dust. Here's just the different gels. This is important for us, maybe not so much for you, but for us, but you see which kind of cross-linking we are using here. We also tested these gels incorporated with polar coating G and with the new nanofluids that were developed in the GREENART framework. And they were, so here is our 2 examples of our gels tested for 40 minutes with polar coating G and 1 hour, and here 1 hour and 1 hour and 30. So following the gel application, we used a swab to perform some mechanical action, but in all the cases, we could remove the layer of paraloid B72 that was on the glass slides using the gel. And the easier, this is the best, not maybe the easier system for us was this using this new nanofluid after 1.5 hours. We also tested the gels on CNF, the CNF gelatin hydrogels on painting mock-ups. So here we have it loaded with TAC 2%. And after our best results are after 3 applications of 3 minutes each. So we can see that the deepest pores of the tissues, we still have some materials to be cleaned, but overall the cleaning was very efficient. This is the CNF alginate hydrogel. So I mentioned the alginate there behind. This is the removal of hydrophilic PVA coating on paper. So we have the gel applied here, another piece of gel here, and we can see here under UV light the area that was cleaned by the gel. And this was also a preliminary test to remove tinted degradation products from paper. And what we can see here is the gel filled with the degradation products that came from the paper. And I think this is the final example. This is another example of the alginate hydrogels. Here they are loaded with water. Here they are also loaded with the new nanofluids. And we can see here that this is for paraloid B72. So we cannot remove the paraloid with water because it's not removable. But then with this alginate gel here, we have the cleaned area if we use the nanofluid. So just to conclude, the Camillas wanted to show you that these nanocellulose and nanolignin derived from sugarcane bagasse are renewable, multifunctional nanomaterials with high potential for cultural heritage conservation, both for hydrogels and for the films, protecting films. They are bio-based systems that can offer high transparency and removability, antioxidant, antimicrobial, and UV shielding properties in the case of the films, and also efficient and gentle cleaning performance for the hydrogels. They are designed to be environmentally friendly and potentially more accessible to conservation professionals in South America and beyond. This is our team working in Brazil. So me, the other Camila, and the students, Isabella and Felipe. And we'd like to thank you very much for your kind attention.
Thank you, Camilla and Camilla, for your presentation, and we are happy and curious to discover the gel in tomorrow's workshop. Our last presentation will be Romain Borde. Romain Borde is currently leads a research group in the Applied Division Chemistry at Chalmers University of Technology in Gothenburg, Sweden. Your research focus on fundamental and applied aspect of soft and dispersed system. 10 years ago, you start an exploration of novel surfactants and nanomaterial for conservation, more especially nanocellulose and silica-based material. You now extend the reflection to preventive conservation application and even on corrective application with your presentation, development of green dispersion for consolidation of encaustic painting. You've got the mic.
Thank you. I'm very happy to be here. We'll just put the first slide. Yes, I'm very happy to be here to present the results of the work we have done with GREENART. In the short introduction, it was said that I started to look into the aspect of cultural heritage conservation some 10 years ago. I can only blame, if you're not happy with that, you should blame Professor Baglioni, who dragged me in some 10 years ago about that. He will speak later, so it's easy to blame him. And we have been looking at very many different aspects. I was very happy to be just after the camellias, essentially, because they paved the way very nicely in promoting how nanocellulose could be a valuable tool in conservation science. I'm a very happy supporter of this idea, and I will try to demonstrate that today. So the results today are basically the design of new and green dispersion, or green dispersion for the consolidation of encaustic painting. And that was the work done by Yiming Jia, a postdoc of mine working at Chalmers University of Technology. Yes. So one of the things on that topic, I was completely ignorant of that topic when we started the project. And people at the Peggy Guggenheim collection in Venice came to us and asked, okay, we have this challenging material, it's encaustic painting. And I was happy, I know, and I said, encaustic painting, very interesting. Well, at the same time, I was nearly Googling what it was, to be very honest. And that's a reality when you're a surface chemist, not a conservation scientist. And basically, the idea was, okay, we have a challenging material. The material is hydrophobic by nature. It's made of beeswax. Underneath, there is a substrate onto which it's supposed to be attached that is lignocellulosic-based material. So how do we combine things that don't like the same things, essentially? That was the question we were addressed. And then, well, as a surface chemist, we came with this proposition to say, well, we can probably take the material you're interested in, the beeswax, coat it with nanomaterials that are cellulosic-based, and then on the top of it, put some polymers that will help us controlling some of the properties of the bulk to regulate the potential for application and so on. And in that case, when working from my field, you look at cellulose derivative very obviously, because they have been extensively used in the coating industry. And I work closely with Norion, who is also part of the GREENART project, and they are producing cellulose derivative. So by doing this, we sort of cut on the challenges, and we avoid working only on natural adhesive, well, such as starch of animal glue that have a tendency to also degrade and are not necessarily the most stable system. We will work with very pure material, essentially, but are still bio-based. And we don't work with synthetic adhesive. That was at the origin of why people at Peggy came to us and asked us, okay, we've been using Aquazole, that was a good material some 20 years ago, but maybe now we need a better solution for it. And well, can you consider doing something about that? So that was the idea and how we started, essentially. So with that in mind, we had to sort of face the challenges of incompatibility. Having a decent surface wetting, we need to make sure that when we apply the stuff on the surface, we will wet. And one of the challenges, you want to make it green, working with water. Water is bad at wetting anything but paper, essentially, I would say, especially encaustic painting and beeswax. Water is not good at wetting beeswax. The droplets do not spread. It will remain on the surface. We need to have a good adhesion to overcome this weak adhesion issue, and having an ease to operate the system and avoiding new deterioration. So on the right-hand side, you have basically the approach that we have been taken. It's relatively simple, but that's here that kicks in the nanocellulose and the cellulose nanocrystals, essentially. Because historically, we have been working extensively on showing that, yes, with cellulose nanocrystals, and if you play a little bit with the colloidal properties of this type of particles, you can emulsify a lot of different things. And in that case, we can just melt the beeswax, make an emulsion stabilized by CNC, so essentially we have a droplet of beeswax that is fully covered with cellulose nanocrystals, so in a way we solve the incompatibility problem, because the beeswax and the CNC, they can like each other to some extent. CNC has it's a colloid that has some facets that are hydrophobic, and if you place them properly, that could work. And then, And then if you want to control and regulate the rheology of the system, adding this hydrophobically modified cellulose derivative, ethyl hydroxy ethyl cellulose, we can increase the viscosity and control that. So that is a little bit the sketch of what we believe to have in solution. We have the droplet we are interested in. They are covered with cellulose nanocrystals. We have the polymer that is free floating, and the beeswax is basically making the particles. So we started with the first question, how is it going when we make the emulsion? So we prepare different type of emulsion with an increasing amount of beeswax in the system. We kept the amount of cellulose nanocrystals constant, about 1%. There is a little bit of a need for a spice. In that case, the spice is calcium chloride because it facilitates the emulsification greatly. So we did the emulsion, and as expected, we see that we have an increase of the average size of the system. We have a trimodal system, big particles, smaller droplets, and this is the cellulose nanocrystals. But overall, what we get is the more we put beeswax in the system, the bigger get the droplets to be. This is expected, nothing new under the sun here. We're pretty happy with that. So in that sense, we started to think, okay, now we want to regulate some of the other property. How is this hydrophobically modified EHEC, ethyl hydroxy ethyl cellulose? I will keep calling it EHM because it makes my life simpler. And well, we looked into that properties. But first we looked at the essentially how were the droplets we created made of, because our naive view on it was that the droplet should be plain beeswax droplet covered with nanocellulose. With optical microscopy, we cannot see the nanocellulose, too small, but still, we didn't expect this kind of inclusion and this type of void that we could see here, essentially. And that means, well, there is a double emulsification process going on that comes from the beeswax that has probably slightly hydrolyzed along the way, so it gets to be surface active. There is some free fatty acids that help in the emulsification. But then we make emulsion that have potentially a void in the middle when they will dry, when they will crack. And that is not a bad thing, because that will enable some breathability of the system. So that means if we look at permeation of the system, this is not too bad, essentially. So that will not clog everything like other film would do. That was a positive surprise we got here. We looked naturally at, okay, when we do the emulsification, it's a relatively mild process, but things can always degrade, so we look at the infrared spectra. I will not dig into the infrared spectra because the bottom line here and the conclusion here is that, well, not much has happened to the beeswax. It's more or less the same beeswax as we put in the vial when we do the emulsification. So from that on, we know that what we mix remain what we mix, essentially. Interestingly, I discussed about the wetting properties and the properties of the film formed by our formulation, how are they behaving and performing. And one thing we discovered by doing that, so we did simply drop casting of the emulsion on the surface, on the glass surface, we let it dry, and we measure the contact angle of water. That is as equally complicated as that. But then what we discovered is that we could achieve very high contact angle system in that case. And interestingly, we started to spot a very neat feature, that is when we have the pure emulsion, like, if I'm not wrong, one of these over here, or even this one, this is the simplest example to discuss, beeswax 5 weight %, 1 weight % CNC, and then EHM in it or not. We can see that if we only have the emulsion that is still beeswax based, well, it has a good hydrophobicity, but rapidly the contact angle decreases. So that means water gets uptaken by the system. Even though it is beeswax, because there is a lot of nanocellulose, it's still hydrophilic per se. Now, when we start to mix that with the hydrophobically modified cellulose derivative, we boost significantly the hydrophobicity, and more importantly, it remains very stable over time. So that means if we have this formulation, we apply them on a substrate, they are supposed to stand and withstand water exposure for quite a lot of time. So that was a bit unexpected, and we're very happy with it. Well, of course, the original idea when introducing the EHM was to regulate the viscosity of the system. This is a very viscosity modifier extensively used in industry, in the coating industry. And well, here what we did was pretty simple. These are the original emulsion with 2%, 5%, 20% CNC content is the same, cellulose on the crystals is the same. The viscosity are, say, well, below 40 centipoise. But then as soon as we start introducing the EHM, like we do over here, we multiply by very large factors the viscosity. So we get from something that is runny to something that is very thick, to an extent that if we do the right formulation, we can have viscosity that are close to a paste. It's nearly close to butter as compared to a fluid that you can brush or spray even. So we can regulate very carefully and very accurately the properties of the system simply by adjusting the concentration of the cellulose derivative while maintaining the concentration of beeswax relatively high, which is useful. So with that system in mind, we were pretty happy, and we thought, okay, now it's time to do something useful with it because we have been working on the emulsion, and let's see what we can do next. So the first type of testing was, okay, we developed that to glue encaustic painting that are delaminating from a wood substrate. So let's see if we can use that as a decently good glue, essentially, because then we are playing with all the possible interactions at play, from hydrophilic to hydrophobic interactions. And this is what we did here. Here you have the results from the tensile testing, the failure load at break, essentially. And we attach two pieces of wood. Well, here there are extension to attach it on the clamp of the tensile tester. And then we put and we measure how much force we need to break it. So the better the glue is, the higher the force is meant to be. And essentially this was the Aquazole 20%, so that's a pretty thick liquid to work with, probably higher than the usual concentration it is worked at. Well, that is the one that is the best. But our system come close to it, and we still have a very strong resistance, and we have a very good efficacy of the system in working as a glue. On the top of it, contrary to Aquazole and some other polymers, we are still very hydrophobic. Here we have just some other type of consolidants that we could consider. If you take Aquazole much more diluted, so 10 times lower in terms of dilution as compared to this one, well, we get a much meager result in terms of performances. So from that we were happy, and we thought, okay, we have this emulsion may affect the color and the properties of the substrate. So we did some colorimetric measurements. If we look here, we have the pure beeswax. Essentially here we have the Aquazole. So the delta E star is much higher. This is our most concentrated 20% of beeswax, but if we start diluting the amount of beeswax, we can really recover and be nearly invisible or much less visible in terms of appearance. So we were pretty happy with that. And of course, if we keep diluting, we can get something that is very, very light in terms of appearance. So far the system was, okay, it's gluing, it's not affecting too much the appearance, and at the same time, let's see how well it will age, because it will be exposed to light, it will be exposed to temperature variation. So what we did here was to look at, okay, let's look simply at the appearance, and we will age the paper. We took Wattman paper, we coat it with the emulsion, and we expose it to UV and temperature. So essentially the bar are for the UV, and the temperature is the symbols over here. And we can see that as a function of time, the system is barely getting modified, and essentially there is no major modification in terms of appearance, which was positive. That means we have a stable system against exposure to environmental stresses, so to say. Then Yiming got a bright idea, because I can only give him credit to that and say, okay, we need to understand how the system is standing water exposure, essentially. And that is not because it's people from Venice who asked us about that. It's not planning to get the stuff under the water, but still, that was a joke we commonly do. And we basically took mock-up. So these pieces that you can see here that have detached were actually beeswax and red ochre dye or pigment dispersed. We coat it or attach it onto a piece of wood, and then we expose that underwater. And you can see it's very small, it's very small. Some of them are only pure aquazole, the one at the bottom. Some of them are cellulose derivative or just the beeswax as well. And very rapidly, as time passes by, we can see that some of them are getting detached progressively. At the end of the day, what made us very happy is that the two only ones that remain attached after 300 hours essentially were our beeswax formulation that contains the cellulose derivative, the EHM though, the CNC and beeswax. And that was the one that we're really boosting. So if we only use the beeswax as such with the cellulose and the crystals, this is not enough because the system is still too hydrophilic, even though it's 90% beeswax at the end when it is dry. We need to have this cellulose derivative that will accommodate and arrange itself to make things going the way we want. At the same time, we were happy with that. We thought, okay, we need to be able to demonstrate that the system has this breathability that we thought we had. So we did water vapor transport measurements. This is a pure layer of beeswax, so nothing goes through a beeswax essentially. And when you compare with our formulation, you can see that, well, we have a decrease at the beginning over the first hours, but then it stabilizes and it remains pretty constant. This is most likely due to equilibration of the system. So that means we have both water resistance and breathability, which was actually pretty great. Then we thought, okay, but humidity is not changing like night and day. It's not like you put it in water. There is variation, small variation of humidity daily, and that is important. So we conducted a DMA, and the conclusion of the DMA is that even though the system will adapt to changes of the plywood or the wood behind it, with time it will follow and it will not suffer from that. So the formulation, because of their colloidal nature, particulates that are not forming a film, are very well handling the variation of extension when we vary the humidity. And they are not much affected by the humidity. Then, based on that, we were very happy, but still the particles I was showing you now were like 40 micrometers. So they are gigantic particles, 20, 40 micrometers. So that's, well, even though they have an attenuated effect on the surface, they may still be visible, and that's nothing we want to work with. And we got the idea of saying, okay, but you know, in emulsion science, you can push the boundaries and make emulsion from regular emulsion to nano emulsion to make them much smaller in sizes. And then we thought, okay, let's make nano emulsion for that. So there are different ways to do them. Since we have some Greek partners in the GREENART project, we thought, okay, let's use the Ouzo effect. No, I'm kidding, that's not the reason. The Ouzo effect is a natural self-emulsifying effect to achieve smaller size, and that is usually working really well. So basically what you do is that you take the beeswax, you dissolve it in a solvent that has a certain miscibility with water, and then you will dropwise add it to water. And then you will form small droplets, much smaller, because it's a self-emulsifying system. The solvent that is miscible in water will diffuse in water, and only the beeswax will remain. And well, we thought, okay, that could be interesting. That's very small particles. They are, well, you can see on that SEM picture that they are in the micron size or even smaller than micron size on this micrograph, essentially. And eventually, by using the same type of formulation, we have something interesting. But in that case, the cellulose nanocrystals are not adsorbed by definition on the surface. It's a free-floating element, as EHM is. And we have other type of interaction at play. Bottom line, and quickly here, we thought, okay, this is a very nice system, but we can use it for canvases, for instance, because canvases have been historically treated with wax, for instance. And here, maybe we can do something about wax. So we took some regular canvases threads. We did an, We did an accelerated aging. So basically, this is the result of the accelerated aging. We decompose the cotton in order to make it weaker. And then we apply our nano emulsion onto it, simply a spraying and so on. And what we can clearly see is that, well, we restore essentially some of the mechanical properties. We reduce the strain that is due to the loss of the mechanical properties due to aging. And at the same time, from this plot, you can see that we are basically increasing substantially the wettability of the canvases after such a treatment. So that implies that the treatment makes it reinforce it, and at the same time makes the stuff a little bit strong, a little bit more hydrophobic, which will make it less prone to sensitivity. The extra good news that we had with that one here is that, well, when we look at the delta E star in terms of colorimetric measurements, well, this is our beeswax nanoemulsion, and we can play with different type of nanoemulsion concentration, and we can significantly reduce to below 1, so meaning we will barely see it on the back of the canvas. Well, the back on the canvas, you barely see it most of the time, but at least in that case, it will be even difficult to see it if we look for it. That was my last slide. I have a conclusion here just to illustrate that what we have done was to look into how to emulsify beeswax and to not use beeswax as such by simply melting. We can really make a colloid out of it. We have done all the characterization needed to understand how the system behaves, and it has a good tendency to restore the mechanical properties of, well, first the encaustic painting. It can work as a glue, but it can also work for reinforcing textile-like material. And on that, I thank you for listening.
Thank you, Romain, for your presentation. And we have some time for a quick 10-minute session for question and answer. So if you want to start with the first question, please raise your hand. And thank you for introducing yourself.
Hi, my name is Emmy Kim, and I teach artifacts conservation at Queen's University in Canada. I have a question for Gabriella. My question is regarding coating thickness, and I realize it might be different between your shiny silver samples and the archaeological ones with the patina. But you used B72 as your benchmark, so I'm curious, how did you apply the B72? Because it's notoriously a little difficult to apply, especially on shiny samples, and get an even coating without bubbles. And how did you measure, or did you measure the chitosan thickness? Thank you.
Okay, so thanks for your question. Regarding the thickness of the coatings, actually we typically use for laboratory validation about 2 microns. And regarding the way to control the thickness, in order to have a thickness which is comparable between benchmark and biopolymers, we usually apply by drop casting the same amount of solution. So we know the concentration, and then we measure the thickness just to be sure that everything is okay. And so we compare the protective efficacy by using a similar thickness. And then the next question, sorry.
B72, how did you keep it from bubbling?
To avoid the formation of bubbling, okay, we just prepared the solution by magnetic stirring, so we have some bubbles. Regarding to avoid the formation of bubbles, just we keep the coatings to dry at room temperature, so we didn't observe the presence of a high amount of bubbles, at least not by scanning electron microscopy and not by optical microscopy. So when we keep the coating drying slowly, so the room temperature, and we didn't observe the formation of bubbles.
I'm Melissa David from the Metropolitan Museum in New York. I have a question for the first speaker, Giuseppe. Actually, 2 questions. The first one is on the coating, and I was wondering if you could say a little bit more about that self-healing property and how that would apply for a coating on an artwork. How would that happen? And the second question on the polyurethane foam, I was wondering if you could say something, if you have tested it, about the aging of these foams and how they would interact like in the medium and long term with artwork, because usually polyurethane are not so good in terms of type of foams and plastics, so if you could say something about that. Thank you.
Thank you for those questions. So regarding the coating, the self-healing properties is given by additives added to the coating that is made of polyurethane. That polyurethane is made of materials that once they have separated, they can recombine. As I showed in the picture, that maybe it was a bit only too much of a schematic reprocessing. Once it is heated up to, I said 100, I checked, it's 130 degrees. And we can apply that temperature only if the coating is applied on a metallic surface. Also because once the metal is cast, is obtained, once you reach 130, it doesn't damage the artwork itself. So it can somehow save also the artwork beneath, so the surface is saved. The way it combines is merely chemicals. So once the bondage, the bonds between components is separated, thanks to temperature, they have the ability to recombine, thanks to, again, the chemistry characteristic of each chains of the polymers. So they have functional groups that react once they are reprocessed. About the polyurethane, yes, is a good question, also because the main problem with the storage with the polyurethanes with artworks is that usually they have solvents and they have the VOC, the volatile organic compounds that can interact with the artwork, and in this way we can have some problems with the materials. But that's why we are starting to use bio-based precursors. The problem is that with the petrol-derived precursors, you don't have only the two components reacting with each other. You also have of course, catalysts, additives, and others. Also, other than playing with the chemistry of each component, we also can play with the fillers that we use to be dispersed into the foam itself. We have focused, I didn't report it, sorry for this. We used also zeolite and other kind of fillers that basically are able, also diatomite, that are able to gather the chemicals that are not good for the artwork. Of course, we are working on the percentage of this kind of filler that are going to be dispersed into the foam. Now we are working with a very low amount just to see if the reactivity between the two components with the catalyst is still guaranteed. Working with the higher amount, maybe it can guarantee again some reduction with the volatile compounds emission. I hope this answers your question. Okay.
Do we have another question? Cannot see very well. Angry? Okay. Okay, so if there is if there is no more question, thank you for all this stimulating presentation to all of you. And it's now time for a free lunch for the audience. And I invite all the speakers to join Eleonore and Antonio front row so we can have lunch together. And we will be back at 2:30 straight, because we will start right on time to be on time for the day. Thank you again, and enjoy your lunch break.